Dear student, I am Dr. Harel Thomas, Professor in Applied Geology, Dr. Harisingh, Gour, Vishwavidyalaya, Sagar. Today, I will deliver my lecture on different type of metamorphic reaction. In this lecture, I will proceed under the following heads: continuous reaction, solid-solid net transfer reaction, mixed volatile reaction, terminal reaction, ion exchange reaction, and finally summary. Hope it will be useful for you. Try to be regular in course. Volatile conserving reaction. The talc breakdown and anesthetite and anthophyllite form Mg3 Si4O10 OS twice plus 4 Mg SiO3 give rise to Mg7 Si8 O22 OS twice. This reaction can be said to occur at the boundary of amphibolite gaulite phases. This reaction can observe in triangular diagram MgO, SiO2 and H2O at its corners. The other reactions are 2KFe3 Al Si3 O10 OS twice plus 8 Al SiO5 plus SiO2 give rise to 2KAl thrice Si thrice O10 OS twice plus 2Fe3O4. Anite plus selemonite plus quartz give rise to muscovite plus magnetite. Solid fluid reaction, devolatilization reaction or net transfer reaction that involves the liberation of a volatile phases H2O for dehydration reaction or CO2 for decarbonation reaction. Example of dehydration and decarbonation reactions are dehydration reaction involving H2O are called dehydration reaction. Muscovite plus quartz give rise to potash feldspar plus selemonite plus H2O dehydration reaction. MgOH twice give rise to MgO plus H2O brucite give rise to periclase plus water. Some dehydration reaction appear to be proceed faster by the path 7 talc give rise to 3 anthophyllite plus SiO4 plus 4H2O. Tremolite give rise to diopside plus anesthetite plus quartz plus water. In these reactions, the volume of the fluid phases varies and continuously as a function of pressure and temperature as shown in the figure. Decarbonation reaction, the solid gas reaction which involves CO2 are called decarbonation reaction. Calcium carbonate plus SiO2 react and form CaSiO3 plus CO2. Calcite plus quartz react and form wollastonite plus carbon dioxide. that is a decarbonation reaction. See figure. Univariant character of the decarbonation reaction calcite plus quartz give rise to wollastonite plus CO2. Change from univariant to divariant reaction due to dilution of CO2. The divariancy of wollastonite forming reaction is represented by TXCO2 diagram in order to understand terminal and external buffering. Because of the entropy of a fluid is generally greater than the entropy of solid phases, fluid appears on the high temperature side of most such reaction, which the fluid composition is fixed. Then devolatilization reactions are continuous, but if the fluid composition can vary as a result of the liberation of H2O or CO2, then the reaction will be continuous. Mixed volatile reaction. In rock containing hydrated minerals, micas and amphiboles and carbonates, the metamorphic reaction involves both H2O and CO2. The liberation and or consumption of the more than one volatile phases, typically H2O and CO2, in all the metamorphic reaction involving mixed volatiles. We have three variables: pressure, temperature and fluid composition. An example is tremolite plus calcite plus quartz give rise to diopside plus H2O plus CO2. Mixed volatile reaction have the same general shape as dehydration and decarbonation reaction on the PT diagrams. However, they are generally plotted on TX diagram instead of PT diagrams. Other examples are dolomite plus quartz plus water give rise to tremolite plus calcite plus CO2. Dolomite plus tremolite give rise to phosphorite plus calcite plus CO2 plus H2O. Dolomite plus quartz give rise to diopside plus 2 CO2. MgOH twice give rise to MgO plus H2O. Buffered reaction. The degree to which a reaction can buffer the composition of the fluid depends on the proportion in which H2O and CO2 are generated by the reaction relative to their mole fraction in the fluid. In order to understand the effect of XCO2 on the investigation, a plot of temperature versus XCO2 plot, we can understand the phenomena of external and internal buffering. External buffering: if the fluid composition is controlled by the external source, as in open system, the fluid passing through the marble will be in sufficient large quantity and would flush away the mixed fluid containing H2O. The reaction calcite plus quartz give rise to wollastonite plus CO2. This reaction explained by the T-XCO2 plot, see figure. If the influx of fluid of composition XA continued as the rock was heated over temperature range, and reaction will completed at TA temperature. This external buffering is responsible for regional wollastonite production in a small width as the isogard. Internal buffering: calcite plus quartz also contains some pure H2O fluid in pores. When temperature increases to form wollastonite, the fluid becomes rich in CO2. From decarbonation, wollastonite will appear above TA, that is TB, and reaction continue to grow until the fluid shift to the XB before there is further rise in temperature. In this reaction, fluid composition is controlled by the mineral assemblages of the rock itself and known as internal buffered. This result of the assemblage calcite plus quartz give rise to wollastonite will be function over a distance in the field in progress sequence. Oxidation reduction reactions. Metamorphic fluid contain O2, but concentration of this is very small. The removal of this O2 is difficult. Thus, such system maintain original oxidation state almost without change even during progress metamorphism. Within the crust and upper mantle, O2 is mostly in combined form of as silicate and oxide. When minerals that are sensitive to oxidation or reduction, for example, iron-bearing minerals are involved in the metamorphism, the concentration of O2 in gas phase is an additional factor in iron oxides, mainly hematite, magnetite and viscite or iron oxide are the most useful indicators for partial pressure PO2 in the crust. These are reacted with the following reaction: 6 Fe2O3 give rise to 4 Fe2O4 plus O2, hematite give rise to magnetite plus oxygen. 2 Fe2O3 give rise to 6 FeO plus O2, that is magnetite give rise to viscites plus oxygen. 2 FeO give rise to 2 Fe plus O2, that is iron oxide give rise to iron plus oxygen. 1.5 Fe2O3 give rise to 3.5 FeO plus O2. PO2 for these reaction can be calculated by the equation delta GO equal to 19.41 T log PO2 P delta Vs, where delta GO equal to free energy of the reaction under 1 bars, T equal to absolute temperature and delta Vs equal to the volume change of the solid centimeter cube. PO2 and P are in bars. The P delta Vs is very small. It is neglected in the calculation made at 1 atmosphere equal to 1 bar. The above mentioned equilibria within iron oxide minerals have been experimentally and thermodynamically calculated by Youngster in 1959. See figure. The figure shows oxygen fugacity equal to PO2 as the function of temperature. It is clear from the figure that PO2 is controlled by the mineral assemblages in FeSiO system. For example, hematite is stable at high PO2. As PO2 decreases, magnetite, iron oxides and finally native iron become stable. See figure. Hematite occur in some and magnetite in many metamorphic rocks, but iron oxide and native iron does not. This suggests that PO2 in rocks undergoing metamorphism is usually of the order of 10 to power minus 10 to 10 to power minus 40 bars, which is lower than the partial pressure of oxygen in atmosphere. From the figure, it indicates that the magnetite plus hematite assemblages show different PO2 at a definite temperature, but natural magnetite and hematite contain TiO2. Therefore, three phases assemblages hematite, magnetite, ilmenite has different value of PO2 at a specific temperature. If graphite is a constituent in metamorphic rocks, it's create in the presence of H2O at certain PO2 at a given pressure temperature. The curve graphite water after French 1966 is also shown. The equilibria 2 Fe2O3 plus 3 SiO2 give rise to 3Fe2SiO4 plus O2. Magnetite plus quartz give rise to fayalite plus oxygen. If PO2 is lower than 10 to power minus 15 and 10 to power minus 30 bars in the range of metamorphism, temperature, fayalite decomposed to native iron and quartz. 3Fe2SiO4 give rise to 2Fe plus SiO2 plus O2. Dear student, today in this lecture, we have discussed about the different type of metamorphic reaction. I have covered this topic under the following heads: discontinuous and continuous reaction, solid-solid net transfer reaction, polymorphic reaction, devolatilization reaction, mixed volatile reaction, terminal reaction, tile and flip reaction, ion exchange reaction, with example to understand the different metamorphic reaction and its significance. To understand the metamorphic reaction, I believe this lecture was useful for you. For further studies, please read the textbooks, references and links given in the text. Thank you very much.